So right hand rule practice, I'm going to sort of do this backwards. Problem number 15 here at the bottom. This is your basic right hand rule, the one with the grip. Sometimes they call it I call it the hitchhiker's version, where you make a fist with your hand and then stick your thumb out. In this case, your thumb will be pointing towards the left. But we have some conventions here. Let me write those down. So as noted over here to the right, the X means into. Basically, in all the problems we'll be doing is toward the floor. So the circle here just basically contains the X. The X is the important thing. That means into, towards the floor. And the dot means out of or toward the ceiling, towards the sky. So those are the conventions we're going to keep in mind. Now, so applying the right-hand rule, which is in the equation we're basically using here for number 15, is this equation up here on the top, the magnetic field around a wire. It's a circular magnetic field that fills the space around the wire if there's current in the wire, and it gets weaker with distance. So the way we show that is as follows. So I've completed this diagram here. Once again, the circles I have here are really not that important, except for the fact that they get smaller as you get further away. That represents the magnetic field getting smaller with distance. If you look at this top equation, when R gets bigger, the magnetic field gets smaller, gets weaker and weaker the further from the wire you get. But what's more important are these X's. The X's are a direction. They're tangents to a circle. So if you imagine a three-dimensional, it's a circle that goes around the wire, looping into the page, underneath the wire, back up and around, your fingers, basically when you grab that wire, the hitchhiker's right-hand rule, if you grab that wire like a pencil laying on a table, your thumb pointing to your right, your fingers curl around and make circles, and those X's and dots are tangents to those circles. So as your fingers poke into the table, these X's right here are tangential directions to a circle going around the wire, going underneath the wire, going towards the bottom of the page and coming back out the top. So these are where your fingers would point back out the top towards the ceiling, but then your fingers would curl around and go back over top of the wire. So that's how we represent the magnetic field around a current carrying wire. Then we have the right-hand rule way up here at the top with your right hand. It applies to two equations that have three vectors each. You have a force vector, a velocity vector, a magnetic field vector, all three of which are perpendicular to each other. We say there's three mutually perpendicular vectors. We're going to be only doing the cases where they're perpendicular. You can also have a non-perpendicular direction between V and B, and that complicates things because when it's 90 degrees, simplifies things. Sine of 90, which would have to be in here if we were doing this in a more advanced way. But we're doing sine of 90 is 1, so the sine of 90 cancels out of that equation. We don't have to worry about the angle being other than 90 degrees. But in the second case, same equation basically, but it's the force on a current carrying wire. So this is the force on a charged particle, proton or electron, traveling through a magnetic field. This is the force on a wire that's submersed in a magnetic field, if that wire is carrying some kind of current. So the convention is, I'm going to use my thumb, okay, for the force vector. So in this case, there's my thumb, all right. I'm going to use my index finger for the velocity or the current direction, and my bad finger for the B field, the magnetic field. So you always have to have your hand with that perspective, but you're going to be turning your hand or turning your body to get your hand into particular correlation with the diagram you're doing. So for example, I'm going to start with one of the easier ones. Number 10. Every diagram, when you get done, every diagram will look like this. A circle with two vectors. And that circle has to have an X or a dot. So that's what we're going to try to find out here. But these two arrows, the F could, in this case, it's given to you. The F is towards the top of the page, but it could have been towards the bottom of the page, like this one. Here's another possible answer. There's only 4 possible answers, basically. Well, I guess 8 if you change the directions. But there's this one where you have right and up. You could have one where it's left and up. You could have one that's left and down or right and down. That's 4. And then you have either an X or dot in each of the circles. But we want to get these right. So, for example, I'm going to start with number 10. You're going to take it says it's the velocity of a negative charge. Actually, let me start with number 13, because number 10 is an electron, so you have to make an adjustment. Let me start with 13. So you have B, I, and F. So this equation doesn't really matter, but you have your 3 vectors. You just got to line them up with your fingers, and we're looking for F. So what we don't know is our thumb. So, but we do know that our index finger there, and that number 13, has to point to the right of the room or perspective of this paper. I have this paper laying on my table. So I'm doing all this with the perspective of this paper lying on the table. So my index finger has to point to the right. My bad finger has to point towards the back of the room or towards my body, but behind me. has to point towards the back. Automatically, my thumb points towards the floor. So the answer to that one has to be towards the floor. So the force vector, F, is towards the floor. That's the answer. Let me, I'll do number 10 later, but let me go to number 7. So I'll start doing these in order. So in number 7, I'm giving F and I, and I got to find B. I'm using the same equation. It doesn't really matter which equation you're using. It's the same application of the right-hand rule. But what I have to do in this one, number 7, is my F is my thumb. My thumb has to point towards the left. My index finger has to point towards the ceiling because a dot means towards the ceiling. And automatically my bad finger in that case points towards the front of the room. So the answer is B, points that way. These little symbols I have above the B here, this little like half arrow symbol, that just means it's a vector. That's old school notation. Some books still have that, where you have a little notation above it. That means it's a vector. You don't need to write that, but that's just extra. All right, so number 8. Okay, I already know the answer for number 8 is either to the right or to the left, because the last missing vector, the force vector, has to be perpendicular to this velocity vector. So let's practice that again. You might want to pause it and try it yourself. The bottom line here in this case is it's looking for F. So it's F is the thumb, so we're not going to start with that. V, your index finger has to point towards the back of the room. Okay, your index finger has to point towards the back of the room. Your bad finger has to point towards the floor. So I'm kind of turning my body around. I'm just pointing my finger towards the back of the room, my index finger towards my index finger towards the back of the room, my bad finger towards the floor, because X means towards the floor. Then my thumb automatically points to the right. So my answer here is to the right. That's my force vector on that particular charged particle if it's going through a magnetic field. Number 9. Okay, so I'm looking for I. In this case, I have my bad finger has to point towards the front of the room. My thumb has to point towards the ceiling, because F is thumb. So my index finger points to the right when I get my hand in that configuration. So once you get used to these, they go kind of fast. Now let's do one of the unconventional ones. So with a negative particle, you have to change the answer. For example, you start off doing it normally. So your F, your thumb has to point towards the front of the room. All right. Your bad finger has to point to the right, and automatically your index finger is towards the ceiling. So the answer for a proton would be towards the ceiling, but it's an electron, so I'm going to change my answer. And that's why this one's tricky. The answer is X for an electron. The velocity of an electron is towards the floor to get this particular right-hand rule to be consistent. So number 11, we have F, I, and B. So my index finger points to the right. My thumb has to point towards the floor, because X is towards the floor. And automatically my bad finger points towards the back of the room, my middle finger. All right, number 12 is an electron, but I'm just going to do it as if it's a proton to start with. My force, my thumb has to point to the left. The velocity, if it were a proton, would be towards the ceiling. A dot is a proton, or towards the ceiling for a proton. So my bad finger points towards the top of the page, but because it's an electron, I have to reverse my answer. So for a proton, the answer would be towards the front of the room. But it's an electron, so the answer is the magnetic field is this way. We did number 13. Number 14, it's a proton. Bad finger towards the floor. Thumb to the right. F is thumb. X is towards the floor. Index finger points towards the back of the room. And you'll find that actually number 14 is the same as number 8. It's the same problem once you finish it off. And there we go. Practice on the right-hand rule. Good job.